Welcome everyone, I am Dr. Rajesh Singh and in this video we will solve exercise for section 4.2 of the book Bartle and Sherbert. So let us start with question number 1, part A. So in this question we have to determine the limits using theorem 4.2.4, which is nothing but algebra of limits. So using that theorem we can write this x plus 1 2x plus 3. So according to the theorem 4.2.4 we have these results. Limit x tends to c f plus gx is equal to limit x tends to c fx plus limit x tends to c gx. Similarly you can have this for subtraction also. Then limit x tends to c f g of x is equal to, you can take the limit separately, fx into limit x tends to c gx. So we will apply both the results simultaneously. So what we will get? This. We can take the limit inside. So this is limit x tends to 1 x plus limit x tends to 1 1. So this into limit to outside limit x tends to 1 x plus limit x tends to 1 3. So this is nothing but this limit is 1 plus 1 and this limit is again 1 and constant, so 3. So this is 2 into 5, which is 10. So this is how you need to apply theorem 4.24. So you have to take the limit separately for each case. Now let us go to the next question, which is B part, which is limit x tends to 1 x square plus 2 upon x square minus 2. So for this, let us start with B part. We have to find limit x tends to 1 x square plus 2 upon x square minus 2. So this we can write it as limit, according to the theorem we can write it as like this, limit x tends to 1 square plus 2 upon limit x tends to 1 x square minus 2 using algebra of limits. This is theorem 2.4. Theorem 4.2.4. It is also called algebra of limits. So using that we get this, and now limit x tends to 1 x is nothing but 1. So 1 square plus 2 upon 1 square minus 2. So this is minus 3. Now I am leaving the next two questions. You all can do that. So let us move to the question number 2. So what does question number 2 says? It says that we have to determine the limits and we have to state which theorems are used in each case, and we may wish to use exercise 15 also. So what exercise 15 says? It says that limit x tends to c root fx is equal to root limit x tends to c fx. So that means you can take the limit inside the root. This is what exercise 15 says. So according to this I can take the limit inside the root. So let us do question number part A, and part D I will do, rest you can do yourself. So let us start with A. So A is limit x tends to 2 root 2x plus 1 x plus 3. So according to again exercise 15 I can take the limit inside. So I will take the limits inside. So limit x tends to 2x plus 1 x plus 3 using exercise 15, which says that I can take the limit inside the square root. Now using algebra of limits, I can have this limit x tends to 2x plus limit x tends to 2 1 upon limit x tends to 2x plus limit x tends to 2 3. So this is what we have. And now so we have the limit 2 plus 1 upon 2 plus 3. So using limit x tends to c, x is equal to c, and limit x tends to c, a is equal to a. So for constant it is a, and for x it is c. So we have just used that, and this is nothing but root 4 plus 1, 5 upon 5, which is 1. Now let us take the d part. So what is the d part? D part is, we have to find limit x tends to 1, root x minus 1 upon x minus 1. So limit x tends to 1, root x minus 1 upon x minus 1. If I take limit directly, then I will get 0 upon 0. So what I have to do? First I have to simplify this. So I can write it like this, and x I can take it as x plus 1 and root x minus 1, because x can be written as root of x square. So I can use the formula a square minus b square. 1 is 1 square, so I can use this formula. And now these two gets cancelled out. So what I get, this is limit x tends to 1. So limit x tends to 1, 1 by root x plus 1. This is nothing but, now I can, let me write on the next page. So using algebra of limits, I can take the limit to this plus 1. Now using exercise 15, I can take the limit inside the root, and this is nothing but, this limit is root 1 plus 1, this is 1 by 2. Clear? So we have done question number 2. Now let us move to question number 3. So question number 3 is, we have to find limit x tends to 0, root 1 plus 2x minus root 1 plus 3x upon x plus 2x square, where x is given to be greater than 0. So you can see, if I will take the direct limit, then it will come out to be 0. So first I have to simplify the two terms. And how to simplify it? We have to rationalize. So limit x tends to 0, root 1 plus 2x minus root 1 plus 3x upon x plus 2x square. So if you will rationalize it, that is, you have to multiply and divide by 1 plus this I can write as x 1 plus 2x. So now if I will simplify it, what I will get, limit x tends to 0, this will become 1 plus 2x minus 1 plus 3x, and this will become x 1 plus 2x root 1 plus 2x plus root 1 plus 3x. So now next page, what we had on this page, yes. So 1 gets cancelled out, and we get minus x in the numerator, and denominator is as it is. So limit x tends to 0 minus x in the name. Now I can take the limit. So using algebra, first let us simplify it. So So using algebra of limits, I can take the limit inside these. I can take, and using exercise 15, I can take the limit inside square root also. So this can be written as 1 upon 1 plus 2 limit x tends to 0 x root 1 plus 3 limit x tends to 0 x. So this is nothing but 1 and this becomes 0. So 1 plus 0. This is root 1 plus 0 plus root 1 plus 0. So we are getting 1 upon 2 as an answer to this. This is question number 3. Now let us see what is question number 4. So question number 4, solution. So I have to find limit x tends to 0 cos, I have to show that limit x tends to 0 cos 1 by x does not exist, but limit x tends to 0 x cos 1 by x equal to 0, this is equal to 0. So this, for this we will use epsilon delta definition, and for this I will construct two sequences xn and yn such that xn converges to 0, yn converges to 0, but their corresponding sequences converges to different limit. So this is what we are going to use. So first observe that cos t is 0 when t is equal to n pi by 2, n belonging to z, and cos t is 1 when t is equal to 2n pi, n belonging to z. So using this I can construct, using these facts I can construct two sequences depending on this such that, so I will take xn equal to reciprocal of this, so 1 by so 2 by n pi. This is our xn for all n belonging to n, and let yn equal to reciprocal of this, so 1 by 2n pi for all n belonging to n. Then by the choice of sequences xn and yn, it is easy to see that what xn converges to 0 as well as yn converges to 0. Now f of xn which is cos 1 by xn, which is cos n pi by 2, and this is but nothing but 0, and f of yn, this is for all n belonging to n. Now f of yn is cos 1 by yn, and this is nothing but cos 2n pi, and this is 1 for all n belonging to n. So f of xn is a constant sequence converging to 0, f of xn converges to 0, and f of yn converges to 1. So this f of xn is a constant sequence converging to 0, and f of yn is a constant sequence converging to 1. So since we have two sequences xn and yn such that, with xn not equal to 0, yn not equal to 0, such that xn converges to 0, yn converges to 0, but the corresponding sequences f of xn and f of yn converges to different limits. Hence, by sequential criteria for limits, limit x tends to 0 cos 1 by x does not exist, right? This definition is clear. Let me take right here, let fx is equal to cos 1 by x for all x not equal to 0. So this is fx, and let gx is equal to x cos 1 by x for all x not equal to 0. So this is how we have defined fx and gx. Now so now to show limit x tends to 0, x cos 1 by x is 0. So for this we will use the epsilon delta definition. So let epsilon greater than 0 be any real number. So then we have to show there exists delta greater than 0 such that there exists delta greater than 0 such that 0 less than x minus c less than delta c is 0. So 0 less than x minus 0 less than delta should imply x cos 1 by x minus 0 is less than epsilon. So for this, what we will do, we will start with this and we will try to express this in terms of x minus 0. So consider x cos 1 by x minus 0. So this is nothing but, I can write it like this, x cos 1 by x, and this I can write as separately. Now we all know that value of cos lies between minus 1 and 1. This lies between minus 1 and 1, so this is less than equal to mod 1, since mod cos 1 by x is less than equal to 1. So cos 1 by x is less than equal to 1, and this can be written thus. We have x cos 1 by x minus 0 is less than equal to mod x, and which is nothing but mod x minus 0. So if I take delta equal to epsilon, then x minus 0 less than delta will imply this is less than epsilon. So let delta equal to epsilon, then clearly from start it is easy to see that 0 less than x minus 0 less than delta implies x cos 1 by x minus 0 is less than epsilon. Hence limit x tends to 0, x cos 1 by x is equal to 0. So this is the proof of question number 4. Now let us move to question number 5. So this is the last question that we will do in this video. Then in the next video I will do question number 6 to 10, and then in the third of the video I will do question number 11 to 15. So what does this question number 5 say? It says f and g are two functions defined on some subset A of R, and they are real valued functions. C is a cluster point of A, and we have been given that f is bounded on a neighborhood of C, and limit x tends to C, g is equal to 0. We have to prove that limit x tends to C, fg is equal to 0. So what we have been given? We have been given that f is bounded on some neighborhood of C. This is given, and next this is given. Limit x tends to C, g is equal to 0. And what we have to show? To show limit x tends to C, fg is equal to 0. So for this, what we will do? We will use the epsilon delta definition. So let epsilon greater than 0 be any real number. Now since f is bounded on some neighborhood of C, since f is bounded on some neighborhood of C, there exists delta 1 greater than 0 such that fx, or you so since f is bounded on some neighborhood of C, there exists delta 1 greater than 0 and m greater than 0 such that what we will have? Mod fx is less than equal to m for all x belonging to C minus delta 1 to C plus delta 1. So this is our star. Again, as limit x tends to C, gx is equal to 0. So for above epsilon greater than 0, there exists delta 2 greater than 0 such that 0 less than x minus C less than delta 2 implies gx minus 0 is less than epsilon. So this is double star. So what we will do? We will take delta equal to minimum of delta 1 delta 2. Then from star and double star, it is easy to see that what we have from star and double star, 0 less than x minus C less than delta implies two things simultaneously. Fx is less than equal to m and gx is less than epsilon. This you mark it as triple stars. So now consider fgx minus 0, because we have to show limit x tends to 0, fgx minus 0 is equal to 0. So for this we will consider this and we will try to express this in terms of x minus c. So fgx, this is nothing but fx gx, and this is equal to fx and gx. So this is less than, you can take this to be less than m, right? This you take to be less than m. So this is less than m into epsilon by m whenever 0 is less than x minus c less than delta using the triple star. So this is, so what we had, thus 0 less than x minus c less than delta implies fgx minus 0 is less than epsilon. Hence limit x tends to 0, fgx is equal to 0. So this is all I have in this video. In part 2 of the video, I will solve question number 6 to 10 of exercise 4.2. You can all subscribe to the YouTube channel so that whenever I will upload the next part, you will get the alert and you will be able to see the video and you will not miss it. So do subscribe our channel. Thank you.